Hi, my name's Conrad from Team Inspiro, and we're tackling the Origami Challenge. We have a great team that came together on the night. We had a diverse set of skills which complemented each other, and we shared a common vision. The challenge asked us to use the origami-inspired space-saving methods as well as elements that are recyclable and configurable. We proposed the following project: a gravity research platform, a better spin on sustainable space exploration. Our mission is to establish a gravity platform for future exploration and research endeavours. Why? It's in line with NASA's strategic plans, which include increasing knowledge, expanding humankind into space, as well as furthering further space exploration and creating a commercial space industry. One of the challenges that you're faced with in space is zero gravity. It has physiological effects such as bone density loss, muscle atrophy, fluid distribution within the body, and eye damage. But we have a way around this, and that is spin to simulate gravity. Here are a bunch of previous concepts, including toroid and cylindrical, but we have a new way to spin.
Thanks, Conrad. What you'll see here is a twin spiral space station. You'll see that each lobe connects to the previous one. What this means is that it can be indefinitely expansible, and we can start at any size, and it also means it's symmetrical about its axis. Why do we want a spiral? Well, the Coriolis effect is pretty weird, and our aim is to achieve more Earth-like conditions and this health effects of gravity in a more intuitive environment. So let's go on. How does the Coriolis effect affect people inside a station? If you walk in the direction of the spin, that means you're moving faster. It makes the force harder, and it's like you're walking uphill. Vice versa, if you walk against the spin, it's like you're walking downhill. So we've created a slope to compensate for that perceived incline. What we have is a rotating exoskeleton for expandable habitats, made up of lots of different segments in which we can have a tube that expands. We have flat-packed ribs, which expand and connect to their adjacent ribs. We know that the initial stage can be fit inside a Falcon 9 payload bay with lots of room to spare. And so here's a video of the deployment, where you can see we have this first packed stage. They extend through 180 degrees, and then with additional components we can keep extending the spiral further and further out. But is it feasible? With that, I'd like to hand over to Carl.
Okay, so in order to understand how important and how difficult this is, we do a context study on Nautilus X. Nautilus X was a spacecraft that was proposed a couple of years ago by NASA as a long-duration multi-mission spacecraft. It's relatively inexpensive at $3.7 billion, and its primary uses were stopovers for long missions, i.e. the Moon and Mars, and an emergency station and hospital, as things like surgery are pretty much impossible to do while in microgravity. So, to give you an idea of how much space and weight this thing is going to take up, we've tried to package it in a payload using a stochastic foam polymer-infused composite, which gives us a 70% weight saving of over the bulk structure. There's 36 segments for the stage 1, giving us a total weight of 2.6 tons for the ribbed structure on its own. And then we go to the inflatable tube, which has a bulk mass of 1.34 tons with a 13-meter diameter. So that basically means we've got 59 cubic meters remaining in a Falcon 9 Delta IV class payload, and some 900 kilos left for our extra equipment, such as the ones listed here. Further to that, commercial expansion includes habilitation, astronaut rehabilitation, so you don't have to re-enter astronauts in order to get them back to regular gravity levels, stopovers for long missions, etc. So that's us meeting the Origami Challenge. This is a new spin on gravity research using a flat-pack spiral concept. Thanks.